So this is the SNARS May 2021 presentation after the monthly business meeting. We have Ed Fong who's going to talk with us today and share some ideas on how to build a collinear antenna. He was with us in 2017. We decided to have him back. Welcome, Ed. Great to have you today.
Are you handing it to me?
I am. Over to you.
Okay. Very good. Boy, how do you guys get 46 people at 8 o'clock? Man, on a Saturday.
You run up the propagation on Zoom.
Hey, now, I've met a lot of you folks over at PacificCon, right? You guys go over to PacificCon.
And NBCon, if you had ever been here also.
Yes, the Reno one.
Yeah, when we had it, last one we had was 2019.
Yeah. I remember seeing you, and you guys own a bunch of repeaters, as I recall.
Yep.
Or man, it's
a whole lot of them.
Yep. I'm amazed how you guys do it. Wow, 46 folks. Yeah, I was up in Reno just last year, in fact. Drove up there. Okay, very good. Let's see, what are we gonna do here? Let's share a screen. And I'm gonna share this one. Let's see if this comes up. I think it comes up.
Yep. It's a little narrow, but there we go. Now we see a little.
Like that, right?
Perfect.
Okay, very good. Yeah, thank you very much. Hang on, who was who's the host here now?
Gary, K6ST.
Gary? Okay, Gary.
Barry, B-A-R-Y.
Oh,
Kilo 6 Sierra Tango.
I'm trying to see who you are here. Oh, that's you. Yeah, I see you. Okay, great. Hey, thank you very much. Welcome and good morning. Boy, sure I'm glad Zoom, because if I had to be someplace at 8 on a Saturday morning would be tough. Anyway, okay. My name's Ed Fong. I teach over at UC Santa Cruz. Of course, we're on Zoom these days, and hopefully by fall we'll return, because it's been pretty tough. I tell you, for the students to learn some of the stuff that I cover is very difficult. I've had to water it down quite a bit. I've a lot of students I've never physically met. I wouldn't recognize them if I ran into them in the street. So yeah, it's slowly changing. Everyone's getting their shot, and our infection rate is really down now, and restaurants are beginning to open up. So I think the difficult part is over. Anyway, so today I'm going to talk about how do you make a collinear? That's very curious, because a lot of people say, okay, I made a J-pole. A lot of people make little J-poles, and I made the Ed Fong dual band J-pole, and it works fairly well. How do I get gain out of the thing? I mean, it actually has, a J-pole, as a lot of you guys know, actually has reasonable gain. If it's done properly, it's a very, very good antenna. It's technically 0 dB, but that's because you reference things to a half-wave antenna. Most things, the National Bureau or National Institute of Standards and Technology, gain is defined as a dipole. 0 dB is a dipole, and it turns out a good dipole erected in a proper way is actually a very, very good antenna. In fact, that's the goal of most cell phones. If a cell phone can get a half-wave performance, oh, they would be so happy. The antennas they stuff into those cell phones are minus 6 to 10 dB. So, an actual J-pole, people say, oh, how do you compare with an X200, a GP6, there's a bunch of, the Comets and the Diamonds, the Ringo Rangers and things like that. Actually, if you had a good J-pole, and again, you guys would know this, being experienced hams, actually works very well if you design it correctly. The reason why is the pattern is just ideal for local work, for distance work. It's a good compromise. And sure, you can get a 6 dB gain antenna. They claim 6 dB is probably not quite 6, but it's got some gain. When you do that, when it's high gain, you guys are into repeaters, so you start shadowing right in the bottom view, because the pattern starts beginning to turn into like a flying saucer or a pancake. So you can't get something out of nothing. When you say 6 dB, oh no, you didn't create 4 times more power. You just redirected it. You redirected a lot that would go up into the sky, but now you kind of flatten it down, and so it kind of comes out more in the horizon, which is okay. if you want to, if you want to talk distance, it will go farther from mountaintop to mountaintop. But as you guys probably know, it's a little bit more complex than that because you have to also cover the people in the bottom. So what I found over the past is, you get a 9 dB gain antenna, be very, very careful, or 9 or 12, if it is 9 or 12, but even if it's not, it's 6 dB or whatever, let's say it doesn't meet spec, but it's pretty good gain. Shadowing, down tilt, the directionality is pretty critical. In certain cases, yes, you'll get a stronger signal way out, usually way out at another mountaintop, but usually that's not what you want to cover. You want to cover people locally with handy talkies. And the reason why I understand this is, you think about police and fire, they're all on handy talkies these days. And I try to explain to them, you don't want gain, you want coverage. And that's not the same. Coverage and gain are not the same. Handy talkies, you want coverage locally, typically 5 to 10 miles, good handy talkie coverage. So you really want a good down tilt pattern and not have all your energy sprayed out, 100 miles out, because that's not what you want to cover. So what I found is you want a little bit of gain. It's not so bad. 5 dB or so for police and fire work. And police and fire work is very similar to our work, right? Handy talkies. We have a very similar problem. Yes, we have people with high power mobiles, but the toughest thing is local handy talkie coverage. So 5 dB is usually quite adequate. That gives you the good local coverage and good enough for distance coverage. Okay, so let's start this talk here. So we want to construct a simple J-pole antenna or converted J-pole antenna. And what was the best way to do it and the things I've tried so that you don't try again that don't seem to work. At least I couldn't get them to work. And simple enough and get some gain. This all started, let's see, do I cover this? No, okay. This all started from a grant we had from AC Darty, which is part of, they do ATD alarms and also they do smoke detectors or fire prevention detectors. And how it started was they needed a good antenna, but they needed a lot of them and needed cheap, because if you guys have burglar alarms, the old system was to do through a phone line. Well, it turns out 20 years ago, 15 years ago, they figured out that's not the best way to have a lot of customers on phone lines for your burglar and fire alarm. One thing, people watch all these criminal shows, and the first thing is you cut the phone lines. Well, that's no good. You cut the phone lines, and then the guy breaks in. The alarm company never hears about it. And the worst of all was this: they had gotten together and said, if you pay $10 to $15 for your burglar or fire alarm system, and you pay that to the company, they're not, it's affordable. But what the company sees is a customer pays us between $10 to $15 a month. Half of that, at least half of that, was going to the phone company, because they don't, the burglar alarm company doesn't own the phone company. They need phone lines. So when you sent them a $10 check, what they found was, hey, hang on, $5 of it is going to AT&T. That's not a very wise thing to do. So this is probably 15 years ago, at least. They probably decided, we got to come up with a really good system. They looked into, we got to get away from paying these phone companies half of our revenue. They're not doing much work. They've got the phone line in, and quite often they'll just mux it with your regular phone line, because they have ways where even if you're on the phone, the digital information, which is above audio, you don't quite hear it, sends out to the alarm company. So anyway, they wanted it to be wireless, not necessarily, but get away from the phone company. Well, their committees got together and said, what we need to do is do a mesh network. Mesh networking, they applied for a license and they got it. And it's like 2-watt radios, just like little ham radio, 2-watt. And probably a lot of you guys have fire and smoke alarm systems by ATD, and there's a bunch of other companies, AC Darty and companies like that. They've got if it's a new one, they've got a little antenna, a little transceiver in your laundry room, in your garage or whatever. And it's got a little rubber duck antenna. It turns out that those are at typically 465 megahertz. They were licensed 5 channels, low power at 465, and some of them even have 5 channels at 455. There was like the region that they can use low power. But the idea is it's meshed. It's all digital, so they've got a central control office in the city, and they can have thousands of users, but they're all meshed, and they test them every night. They send signals to every single one, and it all comes back okay. And if you ever go to a ATD control room, they've got these big screens, and every user's got a little green dot. And if one turns red, there's a problem. There's a fire or something. So the alarm has tripped. So anyway, that was the problem. They said, hey, can you make us an antenna? Some gain. We're willing to pay $40 for it, about $40 for it, and easy to erect, no radials, and and what they were doing is extend the rubber duck on the transceiver that sits in the garage. They would get it, if you were in a weak area that we couldn't find another mesh, another close by customer, we'll put an antenna outside. So they would run like LMR 400 and then this gain antenna, not very tall, 3-4 feet tall, and get some gain out of it. And they had some requirements that they didn't want radials. They were using the Comet, I forget the model number, which had radials. They said, we prefer not radials because it looks bad in neighborhoods, plus they break and all this. I said, okay, fine, no radios. And so this is what I came up with. So this is about a 20-minute talk or so. Not even more, 30-minute talk. And now I can have questions later. On Zoom, it's difficult.
Yeah, it's probably 20. We're almost at. We have probably a 20-minute talk with 10 minutes, so we're done by 9 o'clock.
Okay.
Thank you.
Okay, we'll make it fast then. Yeah. So I tried several things, and here's a common way of doing gain is like this. This is done in the 1960s. You start out with a ground plane. And it's called collinear. And what they do is you have coax. Here's the ground radials. Instead of just a quarter wave going up, you put a piece of coax where the center radiator is now the shield, but the ground is shielded. So here's the ground, the radials goes right up. Here's a piece of coax. And then when you go up a quarter wave, you have a half wave delay. You have a half wave element. You flip them. Because now it's in the correct phase. So if you look at where this thing's radiating, the first quarter wave looks like this. The second, and of course, this is really a half wave. It's quarter wave here and quarter wave ground radials. And then you have a kind of a delay, but it's out of phase. This area is out of phase. And then it actually does radiate a little bit from the ground. And then think about it, it's out of phase because you don't want this exposed. It's out of phase with this portion. It'll cancel. That's why you have to cut it off for VHF 18, 19 inches. You got to delay it by half wavelength. If you delay it by half wavelength and then bounce it back again, because now, remember, you could look at here it radiates again. Here's the shielded part. Of the coax, the first quarter wave, so it acts like a regular ground plane, but then you shield it, look at it as you shield it, because you don't want that out of phase part radiating. And then when you come back out half wavelength later, it's back in phase. And then you radiate again, here you radiate again. So now this portion and this portion are in phase. So that's the fundamental principle of a collinear, and you get gain. Every time you add every time you double the element, you theoretically, if you do it all right, you get about 3 dB. So 2 of these elements, you get at least 3 dB. And if you add 4, you'll get 6 dB because it's binary. So next time you want 3 more dB of gain, you need 8 and then 16. So after about 2 or 4, it's beyond returns, right? It's just very difficult to do. It gets pretty tall too at VHF. Diamonds or cell wave, they've really taken these to the limit. And VHF antennas are 15, 16 feet tall for repeaters. And again, you question whether you actually need one like that because of the angle of radiation. Okay, so we could have done it this way. It's pretty tall, but it had radials. They didn't want that, and actually pretty hard to construct. You guys probably seen these before when you tear apart a cell wave, commercial antenna. This is how they look like. Another way of doing it is a very similar way, except you have a quarter wave shield come down. That's your coaxial antenna on the first quarter wave. So here's your first half wave radiator like that. Again, yeah, a lot of commercial manufacturers do it this way. This way you don't see the radios. It just makes it a little taller. So I wanted to come up with an inexpensive way of doing this. We're talking price limit about $40 retail in the end. And that's hard to do because you figure other manufacturers, why don't they do it? They can make gain antennas, but not at that price. So here's another way of doing it. Here's a very common way. MFJ makes these, and you guys have probably used these. So this one uses, it's either a quarter or 5/8. It doesn't matter what you start out with. Well, let's say it's a quarter. This is a UHF. And they put a delay coil there, and then a half wave radiator. I found that this works if you do that coil just right. If you do the phasing incorrectly, you don't get gain. And you guys have probably done this. And these are very cleverly done. It's 19 inches at 2 meters. So it works 2 meters. That just sees a little loading coil. But at UHF, the theory behind it is quarter wave, and then you delay it a half wave, and then you have a half wave out. And it should work. And I'll show you how we got one to work. But the phase in here is very careful, very, very meticulous. Right? If you don't do it right, then it becomes out of phase. And it doesn't work. In fact, it cancels. And I've bought some of these, and MFJ, I think they just copied someone because theirs does not work. I know the principle behind it, but if you don't do it right, it will not work and will not give you gain. In fact, it'll give you loss, because if this portion here is out of phase with this portion here, you'll get lost, cancellation, and a lot of your energy will go up into the sky. Now, Ringo Ranger, again, see, everyone has the same principle here. Ringo Ranger has a modification of a J-pole. I like this one. You guys are familiar with a J-pole here. You have a quarter wave matching section here, where the end of a half wave, which is a dipole, is a high impedance right there. And then how do you match to high impedance to end feed it? You have a quarter wave matching element. It's a short here and a quarter wave down here. And then so up a quarter wave is going to be high impedance. It matches into the half wave, and look, because it does a dipole, it matches into the halfway section really well. It's high impedance to high impedance in the thousands of ohms. And then again, if this is a short circuit here, that's an open according to the Smith chart. 50 ohms is right around down here somewhere, right? 50, it makes sense, right? 50 ohms is closer to a short circuit than infinity. So if this is, high impedance or ideally infinity, and this is 0, so 50 ohms are right about here in this case. For UHF, half an inch, maybe a little less, 3/8 an inch, something like that. And then you match it, you have a half wave, and that's your standard J-pole right here. But you need the half element delay. So I'm sure a lot of you guys use these. I owned one of these. They kind of fall apart. The problem is mechanically they're pretty flimsy, but they do work. You need a half wave delay. So they put, it's got to be 90 degrees, because if it's not 90 degrees, it's going to be in phase with this half wave radiator and this half radiator. You need a half wave of delay where it does not radiate to get it back in phase. So what they do is it's a half wave delay element. It's a quarter wave going out and a quarter wave going in. So it's a delay, but they put it at 90 degrees so it doesn't cancel. There's obviously some cancellation, so it isn't ideal, but it does work. And if you've ever owned a Ringo Ranger gain antenna, it will give you gain. It does work better than a ground plane. About 3 to 4 dBs better than a regular J-pole. So that's one way of doing it. But when you think about it mechanically, that part is difficult. It looks bad too, right? You go up a halfway wave in your antenna, you see this thing sticking out 90 degrees. It doesn't look great. And then when it doesn't look great like that, mechanically, it's hard to hold up over the years to have something stick out a quarter wave at 90 degrees. Worse than radios, probably, because you don't have anything holding it down. Your radio's down here, you don't have the torque. Here you have the torque of this. If you're holding it down here with some clamps, you have quite a bit of torque up there when the wind blows. But it works. It works well, but it's physically difficult to implement, and it's not very rugged. And by the way, that's why you never see these commercially. It will never hold up on a repeater hill. So again, this is the typical J-pole. Yeah. We can construct this out of 300 ohm twin lead. Yeah, we buy all. There's actually we used to construct these things out of 300 ohm twin lead you buy at Radio Shack or at CVS Pharmacy. Now you can't get it anymore. So if you're going to special order, you special order it. 300 ohms, yeah, so the spacing is the same, but you buy much more heavier duty and with a lower loss dielectric. It's a little bit more expensive, but it's designed for transmitting. You have to order it from like Seminole Wiring. It's all custom made, and we order it we order like 5,000 feet at a time, probably 3-4 times a year. We make a lot of antennas. So the trick is you need a half wave delay before you re-radiate to get it back in phase. So it's just a lot of ways of doing it. So I tried this way. Here's the ways I've tried, and I couldn't get them to work. Maybe you guys can, but I couldn't get them to work. You coil, this is the half wave delay element instead of like the Ringo Ranger where I took that, I knew it works. So I said I need a half wave phase. How about a piece of coax RG174 rolled up quarter wave so that the inside, remember coax is actually 3 conductors: center conductor, the inside conductor of the shield, and then the outside conductor. So I said, well, how about this? If I inject a signal into here and not have it resonate, I'll short it out. The signal inside will travel all the way down. I short the other end, quarter wave, and it'll come back out this end, half wave. So the only thing that's in doubt is how much of that signal is going to be in the outer shield. And whatever it is, it didn't work. I mean, it had some gain, but it was not the 3 dB I was looking for, which means this is not a very good half-wave delay line because the outer shield, remember it's 3 conductors, it's not 2 conductors. So it didn't work. So in other words, I added this to substitute for that section because then it wouldn't stick out. I was trying to compress it. And so that was an interesting experience. You make it like here's next to a quarter, so you can kind of fit it into the PVC pipe. So cool idea, but it didn't work. And the other method, I go, well, how about just doing it this way? But then you have no ground is the problem. Just a half wave delay, just a half wave delay coil. When you inject the signal in here, it goes all the way at half wave delay. But then where do you put the shield? You don't have ground up there, right? You don't have a ground up there. It was just a piece of coax in the center. It's worthless because it's just capacity coupling to the shield. Capacity coupling to the shield, but the shield's not grounded, so you don't have a ground reference. And that didn't work. It's worth a try though. Again, this would fit into the PVC pipe. So then I tried this. Now this is an interesting one. This did work quite well, in fact. So what do you do here? Again, here's a J-pole antenna, standard UHF J-pole, quarter wave down here, half wave radiator, and then a 50 ohm feed point somewhere down here. And then what you do is, remember these are high impedance points. This is a high impedance point, high impedance point. That's how you feed it. This is made of twin lead, so you just cut this piece out. That's how the cuts are. So you don't physically need that, but that comes with the twin lead. This did work, and it worked quite well. You have if you have a quarter wave stub here that's shorted, it must be a high impedance at that point. Just like the way you fed the thing, you should be able to unfeed it, right? It's symmetric, right? This is a dipole, half wave dipole here. A center is 72 ohms, 70 ohms or so, and the ends are high impedance. Someone was clever enough to say, if it's high impedance here, I can do a quarter wave stub to drive it, because this is 50 ohms. It'll convert it to a high impedance. It'll drive it for a half wave J pole. But if you have a high impedance point that you're driving, you should undrive or recouple it to another quarter wave stub, because it's also high impedance and it's short here. So then it's back to 50 ohms there. If it's back to 50 ohms, I just feed it through another J pole, 50 ohms, and then add another element, because this is a transmission line and this is a transmission line. Transmission lines theoretically shouldn't radiate. So what you've done is you let it radiate here, you let it go back in the transmission line, which is really just a half wave delay transmission line. And unfortunately, 300 ohms does radiate a little bit, but it's still more of a transmission line than a radiating element. And then the impedance is going to be matched right back out here. And then you have a half wave. So therefore, it re-radiates because it's matched. And it comes back out in phase. That's the voltage distribution. Isn't that cool? It works. It actually works. I was really happy with this. I measured it, wow, it does work. But I mean, in principle, you're not violating any of Maxwell's equation or anything like that. You are just implementing this. You need a delay line, and we just didn't want this thing to stick out because it's just not practical to stick out and think you can make a reliable antenna mechanically. It will break. So this way, this is all slim and trim. It is half wave taller, and it doesn't radiate, but you could fit this all in a PVC pipe. So anyway, so let's see, do I have the results? Yeah, see, this talk is very short. I made it really, really short. So yeah, you do get about 5 dB. In fact, here's a ground plane. You get about 3 dB, sometimes not even that. A good rubber duck at UHF actually does. We found some that worked quite well, but typically you lose about 3 or 4 dB of gain on a rubber duck. And then a collinear, you get about a 2 dB gain because it's a collinear as opposed to a ground plane. 2 elements will give you about 5 dB of gain. So see, and you look at this and you go, can't we just do this again and again and again? Yeah, I did try. At UHF, it's only, quarter wave's only 5 or 6 inches. It's not that much taller. Again, remember I was telling you a point of diminishing returns. The currents get so low at some point that we couldn't measure any major difference. Although theoretically, you should get more gain. On paper you can, but we couldn't measure any difference. So like the biggest bang for the buck is just 2 elements. So yeah, we tried 3. I mean, you need, again, 4 elements to get any gain, right? You've got to double the number of elements every time. And after a while, UHF may be acceptable, but by VHF, it just gets way too tall. And I'm just amazed at the cell wave that makes these. Phelps Dodge used to make them, they're like 17 feet tall for some gain. Yeah, at some point it's just, the trade-offs aren't very good because then you need to construct it really, really durable if you can use it as a repeater antenna. Let's see. So here's our lab here. Took this a while back. We got a new network analyzer. That's an 8753. Pretty old. We just got a new one, a Keysight 5062. That's a pretty cool unit. Does the same thing as this, but we're much lighter these days with LCD displays and it's supposed to CRT. So we just got that. Let's see. Oh, so we started shipping these. We started shipping these to AC Darty. They were pretty happy with it. Problem is, so I went back to this idea of this. I went back to this idea. I go, this should really work. This should really, really work, right? If you can delay that coil, it's 90 degrees. It shouldn't radiate too much. But now, I thought about this. If I can get this to work, it also will be a lot easier to manufacture because you look at this. The problem with this antenna here, and we shipped a lot of these, they liked them, but we have a lot of manufacturing problems. When we make this thing, you make the first J-pole, you tune it, and then you add these sections because you've got to make sure they're exactly a quarter wavelength, quarter lambda. I mean, that's like, for a given frequency, let's say 465 megahertz. Even the variation in the twin-lead dielectric and the way you solder it, you've got to tune every one of these. They go off. You don't get gain. The phasing has to be exact. So we were manufacturing these things, and I can get the first one to work pretty well. And I think a lot of you guys have made J-poles. You can get it to work fairly well. But how do you add half wave exactly? If it's out of phase, you won't get gain. In fact, you'll get loss. So I found, tuning that stub, we would make this section like this, and then you have to trim the top and trim the bottom. And the way you do it is you get the first antenna to work, and then theoretically, if you add this section soldered on, it shouldn't make any difference in the SWR. You shouldn't mismatch it, right? If it's high impedance looking in here and high impedance there, it'd be a match and you shouldn't get any change in SWR. You can do it. It just took us a lot of time. It was just a pain. To make 50 of these was really a pain. And then you got to add the last section. And if you do it right, you get gain. If you do it wrong, the phase goes off. So it took us a while. And so I went back to this idea. Well, what was wrong with this configuration? Well, nothing in a sense. Theoretically, quarter wave here, half wave delay, and then another half wave radiator. I mean, theoretically, it should work. What is the problem with that? Why is it that when I buy it from MFJ, they don't work? And Tram makes this too. They don't give you gain. At VHF, it was fine because this is a quarter wave. But at UHF, we measured this. It was, you could chop this section off and you did better because something was out of phase. So I looked into this. I said, well, what's the problem? Because I like to say you can manufacture this, but it's something with that coil. What I found with this is the problem. This coil here, you cannot space this apart, right? If you space it apart like what that, that's like a rubber duck, right? It's a helical antenna. Is there some, is there a lot of it's some of it's 90 degrees, some of it's vertical. It's both, it's a rubber duck antenna coiled so that it both has horizontal and vertical radiation. So you figure, well, that's simple to solve. You got to crush that coil down. You got to crush it all the way down. You crush it all the way down and then you trim it. That should work. And you know what? It does. We ended up like this. Again, instead of that delay, you have this half wave delay coil. So you make this half wave radiated there for UHF, 12 inches or so, 11 and a half, 12 inches. And then you also start out with 12 or maybe more, 13 inches of coil here, coiled up. In our case, it was 3/8 inch diameter, but you crush it. You cannot space it because then it acts like a rubber duck antenna. And we all know that, it's like not a great antenna, but we use them all the time on VHF. It works. So you crush it all the way down.
And I just want to give you a quick timeline, maybe a couple more minutes, and then maybe some Q&A if we could.
Okay.
Thank you. Please continue.
Okay, well, I'm done then. So you crush it, and then what you do is you get this section of the antenna working, and then you add that coil. You add the coil, and then as you trim it, you get it back into resonance here. You look at the SWR. You trim it until you still have the same resonance. Whatever this was resonating at, let's say 445. When you add this section, if it lowers it, it's too long. If it raises the resonance, it's too short. So you just add it and you trim it from here. And yes, if you do it right, the trick is you must crush that coil. Otherwise it cancels. Okay, we're done.
Perfect. This is fascinating. Let me just start off with the first. I'll open it up so that everybody can unmute themselves. Let me start with one first question. So you're in the lab, you figure this stuff out. How do you actually do the testing to determine that it's working and that the patterns are what they are?
Oh, we only did that on one. We don't do it on every one. No.
And how do you do it on one of them? What's the process?
Oh, we just did parking lot, Sunday parking lot where there's no cars. And we have a good spectrum analyzer, 8591 spectrum analyzer. You get a reference. You just get a reference, and then later you just swap the antennas.
Cool. Thanks. Let's open it up for questions for Ed and interact with them. We got a good 10 minutes or more.
Oh, by the way, so let me tell you. So you can just take this principle and again add them, right? If you want to add another section, it's half wave. So you can make a bunch. It's really convenient to experiment with. You make a bunch of elements like this. Just like this, it's halfway radiated with halfway delayed coil. And then if you want to see how it affects the adder, you just add another section up here, another section. And theoretically, if you do it right, you'll get more gain. Because it gets hard, it's point at diminishing returns is what we found. Anyway, yeah, go ahead, question.
Good. So who has a question or a comment? Just give your call sign.
AJ6EAC, do you have a picture of the finished product?
Not. We sold them all. Hang on. Do I have a?
Okay. All right.
No, I don't, because it's pretty simple. I mean, it just all fits in a PVC pipe. I'll show you components of them. Yeah, the reason why we have components of them is we have the bottoms and the coils and everything all made because we don't know the frequency. It's when they tell us the frequency, then we cut it and trim it. I mean, it's like, let's see. He said it all kind of fits in a PVC pipe. Here's our reference point here. This is for 465. And you got a connector here, and yeah, you don't see much. That's the J-pole part, and then we just add the coil part. The coil part, do I have any left?
We stopped sharing screen. You can see.
Is this? Question again?
Oh, there we go.
I took care of it. I pulled your screen down so they could see all of you.
Okay, sure.
So show the reference point again where you're shown with the pipe there.
You don't see much here. It's just reference point. That's it.
And you have the coil in there, and then you have the top part.
Right. Pretty straightforward. Yeah. I should have kept one. Do I have another? I might have an old coil here. Let me check.
True entrepreneurship.
Last one. I used my last one yesterday. Yeah, it's just a coil made of here. I'll make one. Yeah, so I make it out of number 14 wire. I just make it out of regular electrical wire you buy at Lowe's, like that, 12 inches, and then I make a little coil. I have a form that I make a little coil on the bottom. That's it. Yeah, I sold my last one. We ship a lot of these, by the way. And so I don't know if you know the story. This is how we raise funds in our wireless group. And we do, I think, a pretty good job of it. At AC Doherty, we ship thousands of these. Thousands. And you see,
Just say the names again. AS
So
what? Yeah, you broke up. AS what? TDR what? Just repeat the acronym for the letters.
Oh, ATD alarms.
Oh.
So do any of you folks have fire alarm systems or burglar alarm systems? And if you're in a remote area, you probably have one of these antennas. We have shipped literally multiple thousands over the years to them.
It's Gauge 7 QXE. What's the turnaround on an antenna?
Oh, next day.
Really? That fast?
Yeah, we have all the forms. See, we have all the forms. Let me show you. We have. So all the connectors we have made by the hundreds. So we don't have them built because we don't know your frequency. You tell us the frequency, we put it together. Takes us probably 10 minutes to put one together and then measure it.
What's the longest one you've made?
Actually, I've made the 4-element one. At UHF, it's practical. But again, by the time you get up to 4 elements, it's a point of diminishing returns.
Yeah.
It gets pretty directional. Have you guys ever experimented with gain and collinears? They get pretty directional. You know, it pancakes too much.
There you go. Thank you.
So we found that the optimum point, and Tom Schiller, you guys might know him, he agrees with that. After about 2 elements, you get the best bang for the buck. After that, you struggle because, it's a geometric progression. It's 2, 4, 8, 16 every time you want some gain. And obviously it gets tall pretty quick.
Yeah, I can see that. Yeah.
So it's kind of interesting. It's kind of fun. And yeah, we've done, again, the way we manufacture, we've gotten this thing down to science. I mean, we can make these, but the reason why I don't have any constructed right now is we make them so fast and they're shipped. And the trick is to have all the forms, right? We've got the coax connectors and everything all set to go. In fact, here we have here. I've got the forms here. Yeah, I should have had one constructed. See, here's a bunch of the J-pole elements here. They're just ready to be cut and trimmed because every customer has a different frequency. So we have them ready to go. Just tell us the frequency and then we put them together.
Cool.
They tend to be, Ed, do they tend to be a single band or multi-band?
Oh, it's all single band, all single band. To make it gain multi-band, you see a lot of these antenna companies that have multi-band. We've tried them. If you want a good repeater antenna, obviously go with the single band.
Hmm.
At home, where you have a dual band radio, you're going to have to go dual band. Going with a half wave, the like the design we have, that dual band one, it's fine. But to try to get gain out of that, and there's too many little phasing elements. And you could do it, but I think it's just tough to do.
Yeah, how long for UHF ham for 30, 40, somewhere in there? How tall is the pipe to pull the
Oh, for UHF?
Yeah.
Oh, it's 3.5 feet. See, for 3.5 feet, no radials, that's not too tall. You can handle that. But when things start getting up to 10 feet and 8 feet, that's just too tall. Then you need some guide wires, or else a very, very sturdy tube. But we found, for economy reasons, if you can get it within PVC pipe, where it's nice and inexpensive. The problem with that is, after about 7 feet, you'll need guide wires. It starts bending.
It's pretty wobbly in there.
Yeah, after about.
You put an end cap on the top or something so water doesn't get in.
Oh, absolutely. Yeah. Oh, yeah. You can put an end cap. Yeah, pretty inexpensive, and the materials are pretty much available. So that's how we did it with AC Darty and ATD alarm. It's a cheap way of doing it. Cheap, and then you worry about the UV light and everything. Oh, this stuff. It's been fully tested. This PVC plastic UV. I mean, they make it's the same material they make the 30-year vinyl windows. And I've had vinyl windows here double pane for 30 years. It does not turn yellow anymore. Does not turn yellow, doesn't crack. They figured this thing out 30, 40 years ago, the chemists. Problem is it never deteriorates. That's the real problem. You can't get rid of this stuff. Oh, you cannot all these vinyl windows, I've people replace, it doesn't deteriorate. I mean, they're working on it. I think a lot of chemists is there something you can treat this vinyl that you've made that's so durable, that's indestructible. Can you paint it or dip it, and then it starts falling apart? They have not figured out a way yet.
We got a few more minutes. Kirby or anybody else that has their mic open, you got a question, go for it.
Yeah, KI7ZVX. Ed, what do you do for the high power version? I'm on your website and it shows a 250 watt version.
Yep. Here, let's see. Do I have any? Yes. In fact, what you see is actually the one you see is a 250 watt version. It's a special 300 ohm lead that we buy from Seminole Wiring. That's number 16 wire, and it's got a much more higher breakdown voltage dielectric, as opposed to standard twin lead that's rated at about 75 watts. And then instead of feeding it with RG174, we use RG8X.
Thank you.
Time for another question to anybody else. Just open your mic.
But you guys are pretty prompt, I tell you. 9 o'clock. Most of our meetings go on forever and ever and ever. That's a very efficient.
They'll leave. The way we get so many people in is we get them back out, or they're off to do other things. We'll stick around after the session for a general session of Q&A for anything about radio. So any final thoughts? Let's see, Paul Warner, you got a question?
Yeah, KN6MZT. What about fiberglass? Why not fiberglass instead of PVC?
Oh, you can buy fiberglass if you like. It's about $50.
Will it detune or change your?
Yeah, because the velocity factor is different.
Got it.
Right. So you can use anything you want that's non-conductive, right? And that's you to cover an antenna, you need two things to look at: the loss tangent and the dielectric constant, or the velocity factor. So what it is
that in non-scientific terms, what does that mean?
Oh, okay. But very simple. You figure, can you cover up something? It's clear that you can't cover it up with a conductor. You'll ruin the antenna. So let's say it's non-conductive. If it's non-conductive, there's a loss tangent to it. In other words, if you transmit RF through it, how much of it attenuates? You don't want it to attenuate a lot. Fiberglass is pretty good. We found that this PVC pipe to 200 PSI stuff is pretty good. A quick check, non-technical. This is what we found. One of my master students did this as an experiment. What is a good, what we call radome, something to cover up an antenna? The conclusion was, how do you check? You just cut a piece, put it in a microwave oven for 5 minutes. If it turns warm, it's no good. Right, temperature absorbs RF. If it stays cool, room temperature, That's a good start. That means it passes the first test. It doesn't heat up. Now, so that passes the test. Like PVC pipe passes the test, by the way. So obviously fiberglass passes it really well.
Less expensive than fiberglass also. Probably.
Yeah, fiberglass is extremely expensive. And you probably guys, actually PVC is stronger than fiberglass. Have you guys ever noticed fiberglass, the cell wave antennas? They kind of, you start seeing the fibers come off after about 20 years up on a repeater side. You've probably seen this. We found that happens and it starts deteriorating. PVC pipe is stronger than that. I mean, PVC pipe, I mean, you look at the black stuff that they say should last 100 years for your sewage pipes and everything. It's very durable. The problem is not its durability. The problem is how do you get rid of it afterwards? There's no good, simple way of getting rid of it. Now, how do you test the antenna? You must trim the antenna inside the pipe. People say, why? If you're an experienced RF engineer, I've answered your question, but let me explain to you other folks. It's not obvious. There's a formula, you guys, when you took your general class exam or even your technician, there's a formula called the speed of light, and all antennas are related. The speed of light is equal to frequency times wavelength. C is equal to F lambda. Without complex math, all antennas have to behave that way. C is equal to F lambda. C is the speed of light equals the frequency times the wavelength. So if you enter 3 times 10 to the 8th meters a second for C equals F, let's say 146 megahertz for the frequency. Lambda comes out to be about, if you convert it to inches, about 38 inches. 38 inches, that's in air. And the way you explain this, when you cover something up with PVC pipe, fiberglass, or whatever you use, plastics or whatever, what are you doing to the speed of light? You're not speeding it up.
Slow it down.
Man, if you speed it up, we're multimillionaires. We found something that's faster than the speed of light, right? You should have learned from high school. There's nothing that travels faster than the speed of light. It only slows it down. So if you look at the formula, C is equal to F lambda, you slow it down, and it's called the velocity factor. If the velocity factor of air is 1, and someone says, oh, this velocity factor of this material is 0.8, that means it slowed down the speed of light by 20%. So accordingly, you're not changing the frequency. C is equal to F lambda. We're trying to transmit at 2 meters, 146 megahertz. If the C changes the speed of light, then you have to change lambda for that antenna. So you have to shrink it accordingly when you stick it in that pipe to get it back to resonant. Try that sometimes. Just make a little J-pole and get some PVC pipe. You'll see that as soon as you stick it in, whoa, the resonant frequency just dropped by 3 to 4 megahertz. Yeah, it does.
How do you tune it? How do you physically tune it inside? How do you get in there to do it?
You pull it out, you trim it, you put it back in.
It's not a lot different than building any other antenna, trimming it out of the ground and putting it back in the air.
Right. Except now, since you're going to use it in the pipe, you got to trim it, put it back in, put it, hold it up in the air. Now we have a pretty good, we call it, it's an antenna range. It's nothing fancy, but you just have to calibrate an area because, can you be tuning antennas out in the mountains every time? You could, but you couldn't sell them at a reasonable price. You got to find an area inside, an open area in your house, like a big dining room in the middle. Find something that correlates well. This is all about engineering, test engineering, correlation. Because can you test something to death, like in a rocket? Sure, but it'll cost you too much. You can manufacture it. What you got to do is find a reference antenna that you've tuned way out in the clear. Okay, this is how it is. You find an area. Because I tune these things at night. I'm not going to sit out in the wintertime out in the cold. You find an area in the house, typically, obviously, it's got to be clear. You can't do this. As the frequency gets lower and lower and lower, obviously, the room has to get bigger and bigger and bigger. Fortunately, at VHF and UHF, you should be able to find like a big dining room area right in the middle. I have an area that's
like the one you're right behind you.
You're right. That's the one. Here's the one. Right in the center. This is a huge room here. Right in the center. I know that center. I've correlated it to the outside and the clear, and then that's how I tune it.
Beautiful. Tell us how they get a hold of you or your website in case they want more information or want to know.
Oh, sure. Yeah, just contact me. We're more than welcome to sell. In fact, Barry, you guys have done a group order. That's why I didn't send you the stuff. Right.
Okay, well, send me something and I can figure out how to get it to the club if they want to do group
Yeah.
or whatever. You can build them on your own or you can use what Ed has.
Yeah, building on your own is tough. It took us a while the principles I've shown you to get it to all work right, all the phasing. It's quite an effort, right?
Years ago, Ed, I had one of your antennas, and it might have been the dual bander. It was in a pipe. It was a roll.
Roll up, right? We do a roll up. So you'll notice the principles of this, where you roll it all up, is about 2 to 3 inches longer than the one that goes in the pipe. You'll see the elements, the half wave, the quarter wave, and the match. But then all of a sudden you lay them side by side. This is for the VHF, UHF one. Wait a moment. The roll up one's about at least 2 inches longer. It is.
Is that because of not the pipe and the velocity factor?
Right, because it radiates in air. The velocity factor of air, nothing travels faster than air. So it's a 1. It's called the velocity factor 1. When you stick it in the pipe, it's got to slow down the wave. And it slows it down by 2 inches, basically.
So what's the name of your website?
Just look up Ed's Antennas, EDSANTENNAS on Google, and it'll get you right there. So if you guys, before you order, Barry, I'm gonna send you, because you guys get a club discount. It's about $8 per antenna, so that's quite a bit. I suppose
instead of how much? 40?
40.
That's big.
Yeah, that's big. Yeah,
okay,
and plus you don't have to pay for postage. I could bulk.
Yeah, well, not everybody, but a lot of people are up in the Reno Tahoe basin. So let's see if people are interested.
Yeah. We get plenty of business.
Thank you.
There's no rush. Anytime. Okay.
Yeah.
Okay.
Thank you so much. Yeah. Just hang on. I'm going to stop in the recording and we'll go for the regular thing.
Okay.
This has been Ed Fong for how to build a J-pole collinear antenna for STARS, the Sierra Nevada Amateur Radio Society, May 2021 meeting.